I'm just going to pick up where I left off yesterday afternoon, but this slide has a quick recap of what we were sort of in the middle of doing. So we're sort of looking generally at the problem of representing computations in proof assistants such as Coq, and I sketched the idea of using, there are lots of different design decisions for how to do that, and we're kind of exploring this path of using monads and monadic interpreters to describe the semantics. And so yesterday we sort of went through a little tutorial about monads and the state monad in particular. And at the end we were talking about the monad laws. And we had made this observation that the notion of equivalence is an interesting question when it comes to, well, practically anything when you're trying to formalize things, but monads also. And so to kind of summarize where we were looking at, for a general monad M. Remember, a monad is just a sort of data structure that supports sequential computation. So we have a notion of bind, which generalizes let or semicolon, and return, which sort of ends the computation in a pure way. And at the end of last time, we had introduced this notion of an equivalence between monadic computations, which I'm writing with this type class EQM, and then using this sort of this approx symbol, which I'll overload for all the different monads that we might use. And then to make sure that everything is one of these well-behaved sequential computations, we were looking at the monad laws. So just to remind you, the bind or the sequential composition has to be associative, which we can state using this law. It says, if we run MA, name the result Y, and use it inside of some continuation KB, and then name the result of that X, and then continue, well, we could have hoisted this first let out to the top. So we could have, we're going to run MA first no matter what, so we can sort of reassociate the first computation to the front of the sequence, and that's called bind associativity. And the only new thing here is that we're going to make sure that the types of these things, these two sides here, are both monadic types. They're M of C. And we're going to use our new equivalence on monadic computations to make sure that that equation makes sense for those. And then we had a couple of other laws. So return A just says, well, this is the computation that just simply provides A as the answer. If we name that answer X and then run it and then give X to some continuation, well, we may as well not have named it at all. We could have just run the continuation on A directly. That's what it means to be pure. And again, we're using our approximation. And then similarly, if we name a computation, the result of a computation MX, and then return it, well, since return doesn't do anything, it's pure, that's exactly equivalent to just running M, which is going to return the thing we called X anyway. So those are the three so-called monad laws. And the equivalence that we're working with is just now a parameter as well as the definition of M and the definitions of return and bind. The one new thing that I was ending up with at the end of last time, and I'm using the sort of Coq library sanctioned definition because it helps with sort of the proof automation that would go on behind the scenes, and is this notion of properness. And so the first thing I'm going to do today is just explain what this means. But you sort of already know, because I said at the end of last class that it's the logical relation for this type given that you're using this approximate, that notion of equivalence for the MA type. So it's a logical relation. And this is just sort of Coq notation that tells you. And what this is asserting is that the bind operator that we've implemented respects this equivalence. So if we give it equivalent computations and equivalent continuations for a suitable notion of equivalent, we'll get an equivalent result. Any questions before I show you the sort of unfolding of bind? Good. Okay, so what is bind? Oh, yeah, if you have, was there, oh, sorry, yes.
I just wanted to ask a minor question about the syntax trigger for
Sure, yeah.
So the way we write it is X arrow, your first kind of double semicolon monad. Really does that desugar to binding the first monad with like a lambda that accepts?
Yeah, I showed, yeah, so the question is, what does this desugar to? And I showed the syntax last time, but I'll just say it again. It's bind of m, so m is the first argument to bind, and then lambda x, the x is named here, and then whatever happens to be after the semicolons here. So in this particular instance, it would be bind of m. The continuation would be lambda x, return x. Yeah, good question.
Have you already defined the pointwise relation, or are you getting to that?
That's what we're going to see. So pointwise is part of the Coq standard library for working with relations. And we'll see it on the next slide. Actually, I've unfolded the definition here. So this is a lemma. It's a kind of a trivial lemma because it's really just unfolding all this, this properness notation. So Coq uses a type class called proper to tell you that a function respects some logical relation. And in this particular case, we're asserting that bind, whose type is MA arrow, A arrow MB, respects the logical relation, which is sort of in this funny parentheses beforehand. And so you can sort of line things up. This EQM goes with the M of A. The pointwise relation, where I put an underscore here and EQM, that's talking about this function. So we're going to use the pointwise lifting for the function space. And then the M of B is this one over here. So these double arrows correspond to those. And actually, here's the unfolded definition. If you sort of unpack all of that, it says that, well, assuming for all M1 and M2, if they're equivalent, that's this one up here. And we have two pointwise equivalent continuations, K1 and K2 of this type. So the underscore I put here gets filled in automatically to equality in Coq. So this will be a little bit too strong in some cases because we might also want to have an equivalence relation on A for the sort of most general version of this definition. But in many cases, you really, pointwise equality would say, given equal inputs, the continuations are monadically equivalent computations. Under those assumptions, then if we bind the two components together on each side, we're going to get something that is logically equivalent in the monadic computation. So that's, yes, question.
So does that indicate that we can collapse any length of definition, and so long as the chain is equal to something smaller, they're still equivalent?
Let's see. So this particular law literally just lets us, the comment was, does this let us collapse chains of somehow computations under this equivalence? Well, it depends on what this equivalence means. And we'll see some examples in just a minute. So the state monad, for instance, will support some notions of equivalence that will justify collapsing certain chains of computations in some ways. But in general, maybe not. It could be, it is possible to create a monad where this equivalence, the EQM, is very fine, like it's literal syntactic equality or something like that. And then in that case, you wouldn't justify a very coarse-grained collapsing of the semantics. It would just be more of a syntactic equivalence. But what this law says is that if we sort of, bind equivalent computations in equivalent continuations, then we get equivalent results. And the fact that we instantiate it with proper in Coq, this is a sort of technical detail, but in the proofs, this will justify rewriting with these equivalences in lots of places, and there are tactics that assume, make use of properness, and will search for equivalences at various types and so on. Okay, and the reason why I'm dwelling on it is actually this shift from just sort of equals to this EQM, this sort of approximate equivalence, is like one stepping stone towards being able to prove interesting facts about monads. And we're going to make one further generalization in a little while, where we'll sort of relax the fact that it even needs to be an equivalence at all. In fact, if you look at this definition, I said that EQM was this binary relation on M, and we'll be able to actually relax it even further and in fact change the types. So we might, this is just relating two computations, well, these two computations will both be of type MB in this case. They're both monadic computations that return a value of type B. But in general, we might want to relate monadic computations that return, an integer on one side and a Boolean on another. And we can build up a kind of simulation relation. And sort of that view of things will become useful down the road. OK, so, but for now, just let's think of this as a stepping stone towards these sort of rich equivalences and behavioral relations that will let us describe computations. Good. And this is, again, a little bit of Coq boilerplate, just for those of you who are Coq experts. I said last time that for state monad, the equivalence that we pick would maybe depend on how we implement state. I use Coq's functions for the type of state. Remember, state S is really defined to be S Coq arrow S cross A for the type B. So we're using Coq's arrow type. And that means that we can get away with using functional extensionality to compare Coq functions for equality. If we had implemented state with, say, some kind of map data structure, or we might want a different equivalence there. But all this to say that we have a choice of what notion of equivalence we're considering for our state and so on. And actually, the proofs for all of these, this is defining the instance for all those monad laws and so on for the state monad indexed by states S. And if you sort of look at them, the proofs are all very trivial. They're basically unfold all the definitions and use functional extensionality. So I didn't bother to do much automation. It's just you use equivalence exactly where you need it. And so for state in particular, this equivalence just boils down to, well, you get the same function up to extensionality. Good. What can we do with that? Well, this is where we get to introduce more equivalences justified by the particular monad that we have in mind. So for state, which has the put and get operations, we can justify these kinds of equivalences based purely on the definition of the monad implementation of bind and return, and the definition of put and get in terms of state functions, right? So remember, put sigma 1 just returns the new state. It returns unit. And updates the state. So it ignores the initial state and overwrites it with sigma 1. And if that's your intuition about what put does, well, put of some state 1 followed by put of some state sigma 2 had better be equivalent to just throwing away the first put, because you were running these sequentially, and this is going to overwrite things. So that's the result. So in the state monad, as I defined it with these two effects, these two operations, we can easily justify this equivalence. And in fact, it boils down to just functional extensionality, because that's the notion of equivalence we're using on these states. So it's really kind of trivial to prove this in these cases. But it's still useful. We can, here's another, another law would be, if we get the value out of the state and then put it back, that's the same as not doing anything at all to the state. So I have to put the type annotation here because this is a very polymorphic thing. It's just saying that, well, it's if you read the state and then put it back, you may as well done nothing, which is the same as returning just true. Well, this is actually Coq's unit inhabitant. So it's the solo inhabitant of the type unit, which is the result type of put. And again, This is just functional extensionality expressed as a law like this. What did I say? Yes, put get. Here's another one. So if we put the state and then get it, well, the get is sort of, we already knew what we were putting, so that's equivalent to also just returning it. So we sort of can name it, we can use it twice. So you can justify a bunch of an equational theory for the monadic operations based on the equivalence. And then you can use these as rewrite rules. For instance, when you have a monadic computation describing some imp program, for instance, you can use these rewrite rules to change, to prove the equivalence between one program and another. The semantics of one program and the semantics of another, I should say. Good. And I guess here's the final slightly more complicated one. This is just another generically true law about the state monad. All it's saying is that if we, because in this version of state, every time we call get, get just returns the current state in its entirety. So if we get it twice without changing anything in between, well then S1 and S2 will be the same state. And so if we have some continuation that uses the two values in some way, well that's equivalent to, this is a bad line break, equivalent to, where did it go? Just reading the state once and then calling the continuation on that one value twice, because we've just named the same state in two different ways. Yeah, question? Sure.
So we have a key there that we didn't use.
Oh, this one we do use the K.
The other one.
Oh,
This one, yeah.
oh, this is probably just a typo in my slides. Yeah, that is unused and you don't need this for this lemma. I'll try it. Good. Okay, so this is taking a step towards, you remember yesterday I showed you proving equivalence of imp programs. We optimized factorial and then proved the semantic equivalence. And these sorts of equations, equational reasoning, is one way to make progress towards that kind of goal. Of course, we haven't quite hit all of the things we need for imp. In particular, we need to be able to deal with this issue with looping programs and divergence. And so that's where we're going to head to next. And in fact, there's still more to say because the program transformations that I showed you yesterday were about the syntax of imp programs, right? So we ran an optimizer on imp that changed one piece of imp syntax into another. We proved the equivalence of their denotations as semantics. And so we want to kind of set up our semantics in such a way that building those sorts of equivalence relations is nice. Good. Okay, so before I move on, are there any questions about that? Good. Okay, so we're aiming at solving this looping problem, but I wanted to take a slight detour through something called the free or freer monad. And that's because interaction trees, which are sort of the library that we use quite a bit for building the style of semantics that I'm showing you, is a variant of these free monads. So we'll study the simpler thing first. Just by show of hands, how many of you have heard of the free or freer monad? How many of you would say that you really understand it? Okay, fewer, but still quite a few. Okay, so let me just, I'll sketch you the ideas and I'll try to get through it relatively quickly. Let's come at it from sort of, again, this we're implementing language semantics idea. So here I've simplified things so much that we're in a very toy language where we don't even we have literal values and addition operations. So this is sort of a syntax that only has very simple expressions. And as we saw yesterday, one way to give a semantics to these things is to implement an interpreter, which in this case we can do simply by writing this little evaluator, and it works just fine. We can define a piece of syntax, add val3, val4, and if we run our interpreter on it, we'll get 7, no problem. One way to see what free monads are buying us is via the what's sometimes called the expression problem. So if we come along and say, we had that great language that supported plus, let's add minus as a new operation. Here's one way we could do it. We would just go back and change our syntax of expressions to be this expression prime. We have to add a new case here. We have to add a new case to our evaluator. And that works just great in the same way that the last one did. I can now subtract 4 from 7 and get 3. Okay, so that's fine. But if you start doing this at the large scale, every time you make a tweak to your syntax, if you add times or division or something like that, you're going to have to change all of the passes of your compiler, and that gets to be a bit tedious, even if it's a little bit, it's pretty conceptually straightforward, but it's not very extensible or modular. So how do we get around that? Well, there's a solution that goes by the name sometimes of data types a la carte, which is basically the idea that we're going to parameterize all of that pipeline in some way to let us make it more extensible. And so one way of thinking about this is now, rather than saying that our expressions are add and minus and so on, we're going to parameterize our expression language by a type of, by some description of the operations that it supports that will leave abstract. So we'll keep our value, our constant types, but we'll add a sort of generic operation that says, well, you tell me what the operation is and what to do with the result of that operation as a kind of continuation, and I'll take those two things and build you an expression. So we've done a couple of things here. We've sort of indexed the type by this parameter here, and we've also said how we can kind of build in some extensibility to the interpreter we're about to write so that we don't have to specify all of the details all of the time. Okay, so we're going to call this do the operation and then use, in this case, we're going to assume that all of our operations compute a natural number as a result, because this is the arithmetic fragment of our expression language, and that's how we would build up this. And the result is going to be back in the expression language. So we've sort of mixed meta-level functions. This is a Coq-level function with syntax, and that's the sort of move that we make to get this extensibility. How does it work? Well, now we can just make a single constructor somewhere called plus, so that's the type, and it will have a single constructor that takes 2 natural numbers. And then we could say do add 3, 4, and then in the continuation, we'll return the value of whatever it results. So this example we can think of as something like syntax. This add 3, 4 doesn't have any interpretation yet. It doesn't have any meaning. It's just a constructor. But now we could re-implement our first naive evaluator by just saying, okay, if we write an interpreter for this expression language indexed by the plus type, which gives us this add operation, well, this is more or less exactly the first thing we wrote, right? We return the n in the val case. There's only one possibility for what the op could be. We know that because the type here says the op is of type plus. Plus has only one constructor. So this case analysis can only have an add. And the only thing we can really do is, well, call the continuation on the result of adding those things and then calling the naive evaluator recursively on the result. And this is basically the same thing as we had before, but with weird syntax, and we haven't really gained much by writing things this way. But what we have done is allowed ourselves to parameterize not just the syntax by these operations, but the interpreter. So we can call this, I'm going to call it fold eval instead of just eval, because it's going to be parameterized by the type of operations, so op. And rather than hard coding everything to work with this add primitive, which we're going to interpret by plus, we're instead going to say, for whatever the op is, tell me how to get a nat out of it. And then if you give me an expression whose operations are described by op, we can fold over that tree like this. It's the same thing as before, except that rather than hardwiring the pattern matching on add and doing the arithmetic, we instead just call this, this handler that will tell us what to do for op. And so the handler for plus is actually very trivial. It sort of factors out the pattern match that said, the only possible case for plus is this add constructor applied to integers, and the result is just we do the add. So the nice thing about this is we've sort of pulled the operator-specific semantics out of our interpreter in a way that now this interpreter is generic. If we have another op, if we want to add minus, we can instantiate it differently and get a different interpreter that will do subtraction expressions. Okay? But it'll still evaluate in the same way as before. So it's a little bit more cumbersome. So it's a little bit clunky notation-wise, but semantically it's nice. It's more modular. This version of the expressions indexed by these types also has a notion of sequential composition. We're not quite to a monad because everything is a little bit too specific, but I just wanted to point out that if we wanted to run one of these sequences of operations where all of the ops are described by op and then do some more, well, we could write that as if we have a sequential, if we have one of these expressional operations and we want to do something after we evaluate it, well, the continuation would itself be one of the, it looks very similar to the type in our op constructor back here, in our do constructor. So here's the do constructor. In other words, a continuation in this view of things is a function from natural numbers to expressions over ops. So if we wanted to sequence one of those continuations accepting the result of this expression, well, we can write that as an operation like this, where the only difference is when we get to the value case, we call the continuation as opposed to just returning the value. And otherwise, we sort of, otherwise we have some operation and we apply the handler that we got in the, so H here is the continuation of this op, and we put K after, in sequence after that, that result. So if you look at what's going on here, we're going to run the first operation. It's supposed to continue with H, and then after we continue with H, we're supposed to continue further with K. We do that by providing the continuation, which sequences K after H of n. Okay, and this is not quite a monad, but I hope you can see that it's starting to look like one. There was a question somewhere. Yeah, it was answered. Great. That's what I like to see. Yeah.
So to define a continuation, one can use the full power of Coq, its entire expressiveness. So
Yeah.
I suppose this works just because Coq is pure, and you cannot do much to define the continuation.
Right, right. So the comment is these continuations are Coq arrows. So you have the full power of Coq to write whatever function you want here. I guess the remark is that's okay for this arithmetic language because in Coq everything is so pure that you couldn't do anything except provide a function like this. In other languages, you're right. If this function, I don't know, printed to the terminal or had some other effects that weren't reflected in the type, then you could argue about whether this was sort of a semantics of, or sort of a way of interpreting these operations. I think that's very fair. So in Coq, the fact that everything is super pure means that we can really think of these as kind of just a tree in some sense, where for every natural number, we just have an expression. It's very pure. Nothing else can be there based on the type. Good. So this is fine. We can always do a little bit of engineering effort to make things a little more palatable. So here's a helpful definition. It's just a little, we call it trigger in the iTrees paper. Oh, question. Yeah.
I was just wondering if you could elaborate on the previous slide. It seems like we have our bind.
Yeah, why is it not yet a monad? Well, the reason is basically because here we've fixed this to be a natural number as opposed to some other. The type of bind is M of A, and then it takes an A arrow M of B and produces an M of B. So it's quite polymorphic. It's polymorphic in A and B. But here there's not enough polymorphism in, for instance, this spot. And in fact, this expert op doesn't even return an answer. We've sort of fixed the result type here to just being these expert ops. So it's not quite general enough. But we'll fix that in just a minute. Yeah.
I'm not quite sure why this function definition is allowed, because it seems like you're kind of constructing potentially non-terminating function under the hood.
So the question was, why is this definition allowed? Because it seems like we might have a non-terminating function. This definition is allowed by Coq because it will always terminate, actually. So even though we're calling seek inside of itself, on h of n here, the result ultimately is going to be inductively defined on E. So this, well, I guess another way to say it is this, it turns out this use of seek is always in sort of a positive position in the future of the continuation, and so it will eventually bottom out with a tree. So there's no way you can construct a loop like this. Yeah. We'll have to actually, yeah, so we can't, you could potentially create a loop if you could somehow allow for K to refer to the very seek that it was binding in itself, but that's not going to be allowed by Coq either. Good. So first, let's define, so trigger, just syntactic sugar. So we want to just say trigger an operation. What does that mean? We do the operation and return its value. So that's just a handy piece of notation. And so that lets us write some nicer code. It says trigger add 3, 4 is a computation that will evaluate to 7 when we interpret it with our evaluator. And then we have this sequence. So here, I'm using the sort of monad-like notation already because that's what it's going to be. But this is just our sequencing operator, still too specialized. But x and y here will be of type net, and we're going to return a natural. We're going to return an expression out of all of this. So, this does exactly what you think. It adds 1 and 2, names that x, adds 3 and 4, names that y, and adds those two together. So that's 10 after we evaluate it, right? So this part up here, E2, is in some sense just a fancy way of describing a tree of these constructors that happen to involve this add node. Okay, I don't want to dwell too much on this. Is everyone fairly comfortable with this add stuff? So the benefit is we could play the same game with minus. We can now totally separately define a define a constructor for this type called minus. We could add a handler for interpreting just that kind of piece of abstract syntax, which just will do the subtraction. We could instantiate our interpreter with this handler, and now we can, we didn't have to change the interpreter. We just reparameterized with a different handler, and now when we subtract 4 minus 3, we get 1. Okay, and you might be thinking to yourself, well, great, we can make expressions that have adds and expressions that have minuses, but can we do both at the same time? And the answer is, well, yes, by doing just a little bit more programming, basically. So because our interpreter is so parametric, right, it's parameterized in the type of operations, we could give it a type of operations that is the disjoint sum of the add and the minus operations. So it would allow us to have both of them. And so we could even make that into a nice little piece of notation where we say, if we want to add together or take the disjoint union of two sets of operations, we can do it like this. And now we can write a generic, so we can create an algebra for working with these handlers as well as these pieces of syntax. And so if we have two handlers, one for op1 and one for op2, say add and minus, then we could turn that into a handler that's able to react to either of those events by just dispatching on whether we're in the op1 case or the op2 case. Right? So the idea here is that with a little bit of programming, we can build up an algebra of these different node constructors. And with some nice syntax that kind of hides a lot of this stuff, we can think of it as like literally I want add and plus minus, and then we can write a program. So first of all, we adjust our evaluator to say, it takes this handler for both of the things, so it's handling both kinds of events simultaneously. And then we can make an expression that might have plus or minus events in it. And then there's a little bit of cruft here. We have to say, sub is in the right side of this event type, and add is in the left side. So there technically, there have to be these injections to say which case we're in. But we can express this sort of computation, and that will get us, the ability to mix addition and subtraction together. And in fact, I don't want to dwell on it. Yes, question.
Like, if you know what side of the sum you're on, isn't the tag of add and sub kind of redundant?
Yes. So the question is, if you know what side of the tag you're on, isn't it redundant? And the answer is completely. And the way that we address this in the iTrees library, and you would do this in practice, and they do in the data types a la carte, is you use some type classes to figure out, this is a sub, it's of type minus, it must be in the in-right branch. And that takes you into a little fun exercise in sort of logic programming to figure out how to inject these in-lefts and in-rights. There are some subtleties there because there's nothing about this setup at the moment that prevents you from saying plus and plus again, so having two kinds of plus nodes. They would be distinguished by the left and right. So there are some subtleties. And in fact, for people who are wondering about this is just a little sketch of how you would implement this type class, right? So if we have a way of injecting one kind of operation into another. So we're going to inject the sub operations into the, here we wanted to figure out, just based on the type of sub, which is minus, that it should be on the right-hand side. And so we build a little program that says, well, we can always think of one op as an op as being injected into itself. This is sort of the base case. On the other hand, if we're trying to inject op1 into a sum like this, well, it's the left case, and dually for the right. You do have to be a little bit careful about these overlaps, but I'm simplifying things here a bit. And we could even build this type class search into our definition of trigger, and then you could basically, write code that looks like this, where you don't have to say which case you're in. So that's all sort of, if you're doing this stuff for daily, you want these kind of conveniences. But like from a semantics point of view, it's really that these tagged events tell you which handler you're in. So convenience matters, though. So it's nice to have stuff like this. Good. And in fact, you could go even further, because why do we need to write these triggers? Let's just make some notation for that, and you can sort of see where we're heading here now. I have these things that look like I'm writing sort of monadic code in Coq, but really I'm building up these trees. And so you can go quite far in this game and use Coq as a meta language for implementing lots of little neat interpreters with this sort of strategy. Good. Any questions about that? Good. So I also wanted to point out one other thing here. So far I've been talking a little bit as though this expert type with the indexed operations is like a syntax, and it is in some sense. It's sort of a way of building these trees. But we can also think of it a little bit like a semantics, right? So if I had started with the original sort of naive abstract syntax where this is way back to the beginning, where now we're just going to hard code. Our arithmetic language has values, add and minus as abstract syntax. We can make a function called representation or something like that that goes from the abstract syntax to this sort of parameterized expression tree version. It just sort of undoes the interpretation work that you might expect, right? So how does it look? Well, for the value case, we have a value constructor. For add, what we do is we recursively compute the representations of the subtrees, bind them in our expr type. We have a sequencing operator there, and then use our sort of smart constructor to trigger that node in the tree. And if we do this, you can think of this as, in some sense, like a way of turning an algebraic data type, which is very clearly a tree, into something that's a little bit more, it's tree-like, but has the ability to have these parametric handler style implementations. So we don't have to write our interpreter for all the special cases of this data type up there. We write it like this, where we evaluate the representation of E using our kind of separately instantiated interpreter. And you can build this into, you could do this in stages and interpret just the add things and then just the minus things separately and kind of build up layers of monadic interpretation. And this idea of building up monadic interpreters is quite an old one. It goes back to, I think Simon Peyton Jones had a paper from the 80s on this idea. But it's sort of a nice way of building up complicated interpreters. And it's all still will compute, right? So just to show you, like if we start with very concrete algebraic abstract syntax and compute it using these semantics, we'll get the actual computation. Good. And from that, actually, it's a very short step to free monads, or the freer monad, technically. So what do we do? All of what we just looked at was a little bit too specialized to really be a monad because we had sort of fixed the interpreter to nat, and we had sort of fixed the results to these continuations to accept nats and so on. So the way we kind of make that slightly more general is like this. We still have the same basic two constructors. So we have rather than calling it val, I'm calling it return because it will be the return of the monad. We still have this do operation, and we still are going to parameterize things by the set of operations. But rather than hard coding the op as a type like this, like we saw previously, where it was just give me some type of operations, we're instead going to do a little bit of dependent programming. And there's actually, well, if you're curious, there are other ways, other design choices you can make at this point, but this is what we use in iTrees. So rather than parameterizing this type by just op, the type of the sort of nodes of the tree, we're going to parameterize it by what I'll call the event signature, which is it's a type constructor. And we'll also parameterize it by the return type of the monad. So our return isn't going to be fixed to natural numbers. We're going to be able to return any R here. So this is one of the places we were too specific. And the do constructor is going to work like this. So we think of E here as telling us, given a type X, well, it's indexed, it's a family of types indexed by the results of those computations. So the way to read E of X is, this is going to be an operation that when we interpret it using this fold, will give us back an X. And so before, all of the operations return nat, so plus returned a nat, so it would have, the results in that case were fixed to be nat. Now we're indexing the operation by its return type in some sense. And we're quantifying in the do node, in the do constructor, we're saying, well, if you can find an X and an event or an operation that returns an X, and you give me a continuation that can consume that X and produce one of these free ER things, well, I'll happily construct you a tree that has that shape. Okay, so basically we made two moves. We indexed the whole thing by the result, and then we made the ops dependently typed so that they come carrying along the description of the type that they return. And we use that here in the continuation to say, how do you continue when you're trying to build this thing? Okay? So this is called the free monad, or freer monad technically. Let me just show you how we would instantiate it to do the thing we just saw with the kind of specialized version. So what would plus was just the single constructor type that had one constructor called add. It took two natural numbers. We didn't have to specify. We had assumed that it was always going to return a natural number when we sort of interpreted it. But here, we instead specify that as part of its type. So plus is no longer just a type. It's a family of types indexed by the result. And in this particular case, we use the dependency to say that add is always of type plus nat, meaning that when we interpret it semantically, we'll get a nat. And now we could also have Boolean operations. So we can say that the OR sort of operation takes two Booleans and produces one of these bool ops whose result is supposed to be a bool. So we can sort of encode the type information for the arithmetic or Boolean and any other types you like using this index. And we can also use that type as part of the definition of the handler. So when we instantiated our evaluator, we had to say, how do we interpret the add operations? Well, we're going to have a handler for plus again. Notice its type is going to be polymorphic. It's going to say, for every x, if you give me a plus x, I'll give you back an x. It just so happens that we, as the programmer, know that plus x is only inhabited by add, where x will always be always be nat. And so the only way to kind of instantiate this properly is x is going to be equivalent to nat. And so the typing will ensure that this is well typed. And similarly, we can write a polymorphic looking handler where the result type is specified by, in this case, bool. And so we're allowed to return Booleans in those cases. This dependent pattern matching will tell us that, in the case where bool, where we're matching on an or, x had better be bool, and it works. And now we can adapt our fold, and we'll call this fold pure. We're going to see some more interesting variants of it in just a little bit. But now, really the only change is it's parameterized not just by op, it's parameterized by the event signature E. So that's going to tell us the result types of all the things in our tree. The result type R, a handler, a generic handler for any E of X. It will take one of these free trees and give us back an R. So this really is just a fold over the tree, where when we get to the result x, notice that it takes an E of R, so we know that the return type is of type R. And in the operation case, it's very similar to the code. The code is the same, only the types have sort of gotten a little fancier. So we just recursively fold the same handler over the result of calling the continuation after processing this very operation here with the handler that was passed in. Yeah?
It seems to be aligned here, but implicitly do can return an value of an intermediate type, and that's what's symbolized by the underscore. And that can eventually at the end of the tree
Will be an R, yep. And that's actually, so the comment was, the type here might not be R. It might be some intermediate type on the way to producing an R. And in fact, that's exactly what lets us be a monad instead of something that's not a monad, because we'll have a sequential composition. And this is sort of, in fact, this is going to be very close to bind. And that would be sort of the intermediate state. Remember, we always name the intermediate thing before passing it to the continuation. The intermediate thing is of a different type than the result of the whole bind, and that's the type over there. Yeah, that's a very astute observation. Yes?
So does that mean we're thinking of like, well, maybe I probably missed it, but does that mean like free E is the monad?
Yes. Yep. In fact, free E is the monad. And here is the definition of, well, I framed it as sequential composition. The only difference we'll see between this and bind is just the order of arguments or something like that. But roughly, if we want to sequentially compose some E, which is one of these free EXs, with a continuation that takes an X and does a free EY, to get a free EY, then it's the same as we saw in the sequential computation before. At the leaves, at the return nodes, we just call the continuation. And otherwise, we do the initial operation and bind it with a continuation that does the sequential composition with the leaves. And here's the monad instance for this. It's return and bind. So this sequential composition is the bind of this monad. And the return is actually just this return constructor, which is polymorphic. It's of type for all x, x arrow free EX. Question? Yeah.
So can we sort of think about sequence as like, well, I guess that's pretty much is what it is. It's sort of like collapsing the tree down, like binding two monads into one.
I mean, so let's see. So I like to think of it more as we have a big tree that has a lot of leaves, and a sequential composition of trees says, give me a continuation that will apply to the leaves of the first tree, and I'll call it. So you're building a bigger tree over from the small, so in this particular case, E we can think of as a tree, and this we basically splice in at every leaf the result of calling K on that leaf. So it's a tree in that sense. I'll have a picture of eye trees, and that I think will help clarify that. But this is the freer monad. Yeah, question.
Maybe just in a gap in my calc knowledge, but do those examples you gave, like with addition and all that, do they have the type F free E already? Because I didn't see the type.
These back here. Back here, like when we're talking about these earlier examples don't yet have the type F free E. They have the type expr op. Well, expr instantiated to, well, they have this type, expr plus minus.
Okay.
But we would reframe this as F free plus minus for suitable plus minus. Good. We have to prove the monad laws, which means we need a notion of equivalence for these trees. And here is a definition of what it means for two of these F-free EX monadic trees to be equivalent. In the base case, it's easy. They're free, or they're equivalent whenever they return the same answer at that leaf. And for a do node, I think of these as nodes in a tree, decorated by an op, they have to have the same node in the tree because this is sort of like syntax. So they have to have the same piece of syntax there. You could imagine variants where you related different trees with different types of nodes, but the op, in this case, the root of the tree has to have the same notation. And we want this sort of extensional equivalence on the continuations as well. So K1 and K2 don't have to be literally the same Coq function, but they had better give you the same, up to this EQ-free notion of equivalence, the same trees when given the same leaves. Yes, question?
Does this coincide with equality in the case of function extensionality?
Yeah, so, well, there's a question of what do you mean by, if you're in a world where you have assumed functional extensionality, then yes, it would correspond to equality for the free type, because the only place that's not sort of normal equality would be here, right? So if you're using functional extensionality, that's basically what we're asserting. But this is a little bit looser in the sense that, well, we're going to generalize this in a little bit, and it won't be exactly, we won't require it to always be equality. And yeah, we don't have to assume functional extensionality at all in the long run. Good, and we can prove that this is an equivalence relation. It boils down to exactly what you would expect. And we can prove the monad laws. They actually follow, like this is just an inductive data structure, and you get the exact induction hypothesis you need. So proving that all the monad laws hold is just a matter of kind of unfolding the definitions and looking at the trees and using the assumption here. You're going to get an assumption about the equivalence of the continuations, and the monad laws will work out just exactly as you would hope. Okay, there's one little wrinkle we have to tidy up before moving on to I-trees, which is that before we had this way of adding, plus and minus together as just types. We used the normal in left, in right. We have to sort of lift that to these sort of polymorphic indexed families of types so that they can talk about their return type. But that's not too hard. We can just do programming in Coq to say, oh, we don't want, so the old version of plus was expected these to be just types. Now we're going to take the disjoint union of these indexed families of types, but it's still the same thing. We have in left and in right constructors. The only difference is that now the type of this whole thing, the whole sum, is going to be indexed by the return type. So it's parametric in X, and we use it in both places. And now we can use this plus, this sort of plus prime notation to mean this. And we can sort of replay all the same thing we just saw with a little bit fancier type annotations. So we can now add together two handlers. So a handler for op1 looks like this. A handler for op2 looks like that. We can construct a handler for the sum of these things, which will have this type, where we've redefined plus up there, but the code is just the same. We do case analysis and then invoke the right handler. So we're just sort of indexing things enough to make the return types work out. And we can do all the same game with the implicit injections, and the typecast classes get a little hairier because of the return type stuff, but that's not I don't want to dwell on that. But now we could write, rather than our expr thing before, we can say, E1 is an instance of one of these free monad values where we have plus and boolop. I chose boolop operations this time. And this particular expression happens to compute a nat, but it might also compute a bool or some other thing, depending on what we wrote down here. in this particular case, it's saying, we compute the, well, it's a little silly. We compute the OR of true and false, name that B, do a Coq meta-level conditional test on the result of that Boolean. So here is where we're using the fact that we can write the arrows. Somebody observed that the arrows in our continuations have the full power of Coq. Here's where we're doing it. We're writing a Coq if then else on the Boolean to trigger two different events. So in some sense, this is now mixing Coq level, meta level evaluation, but it'll still compute. So if you just think about what this means, right? This is going to be true, assuming we've implemented OR correctly, and then we'll take this path and we'll get 20. So we can evaluate all of this. Good. So that's so what we did here is we define this sort of indexed monad. It's called, the monad itself is f free of E. So for any type E, well, type arrow type constructor E, f free of E is a monad. Okay. The nodes, you can think of it as a tree where the nodes are given, the shapes of the nodes in the tree are given by E, and we can build the sort of continuations or the children of those nodes using these arbitrary Coq functions. And we can write an interpreter. And I'll just say, somebody had mentioned this, technically f-free is what's called the freer monad, not the free monad. Morally, the free monad would be if we take bind and return and this E here, the sort of parameter, and freely generate uses of those things. That particular definition doesn't type check in Coq because of guardedness. It's hard to show that it's always terminating. One way to think about the difference is f-free sort of always ensures that you've associated your binds to the right rather than letting you sort of arbitrarily kind of build things up. You can see that actually because in our type back here for the do, right, it's not an arbitrary monadic computation. It's not of type f-free ER, which is what the input to the bind would be. It's just an op, which is an EX. So this is sort of like you've right associated all of the monadic operations, but the sort of primitive operations are described by op. So that makes sense. So that's sort of a technical thing, but it's very useful for implementing things in Coq. Okay, good. So that's the summary of that. Good. I'm doing reasonably well on time. Any questions before I move on a little bit? Good. I haven't said how to handle impure computations. So let's play this game of adding sort of state-like events to these trees. So for the purposes of naming things, I'm calling this, so we have a couple of levels of interpretation going on here. So the nodes in our tree, sort of the syntax, I'm going to call them read and write as opposed to put and get, because put and get are going to be the semantic interpretations of read and write. And I'm going to just assume that we have a single cell, which is a natural number. We can generalize this to more interesting states. But the idea here is that the read node is going to be something that gives us as an answer a natural number. The write node will take as an input a natural number, so it's just part of the type of the definition of the node itself, and it doesn't give us any interesting result. It just gives us a unit result. So this is one of our inductively defined. It's a family of events that can appear in our tree, and so now we could have a little monadic computation where we use our free monad to introduce cell events, cell nodes in the tree. But we could also have plus operations. We can sort of mix and match the operations we put into our tree. And in this case, it's just going to return unit as the result. And what does it do? Well, it reads the result of the cell. It we'll call it x. It adds that x to itself and then writes it back to the cell. So the read and the write events here are sort of intuitively going to be interpreted as updating the state, but at this level, it's just a tree with sort of uninterpreted, there's a read node, then there's an add node under each read operation. In fact, this tree we can think of as having a single root node labeled read, and then a natural number of children, one for each possible value you might read from that. We know that because the result of read is a natural number. So it's an infinitely wide branching tree. For each number, we're going to have a little short tree that says an add node, and then for each add node, there will be another child that just has a write operation. Okay, so this is really just trees still at this point. But we can slightly generalize our notion of fold. So before I had specialized fold, so it always just gave you the R, but we can make it a little more general yet. Rather than folding over a tree to get just an R, we can do what's called a monadic fold over the tree and get some M of R for some arbitrary monadic computation. And so how is that going to work? Well, we're going to need, we have our events here. These are indexed types. M is a monad. M is an indexed type, right? So we could build a tree whose events are M's, but we can also build a handler whose results is one of these indexed M's. So this notation with the squiggly arrow is just a handy shorthand for this parametric function. It says E squiggle arrow F says for any result X, we have a sort of event that's going to return an X, and we'll turn it into another kind of event that will also return an X. So this is sort of preserving the return type parametrically. And so now our handler is just, we get an event, we return some monadic computation that's guaranteed to give us the same type. And if we, this is, again, very similar. We fold over this tree. In the return, we just return X. We're allowed to return because we're in a monad in general. So here we've assumed that M is a monad. And for the do operation, well, do is the bind of the tree. We're just going to interpret the bind of the tree as the bind of the monad. So do op k says, well, run the handler on the operation, the description of this node in the tree, to get a monadic interpretation of that event, bind the result to X, and then fold the same handler over K of X. So in some sense, I like this the best because it's the cleanest, simplest version of all these different interpreters I've shown you, but it's also the most general, right? So this will take one of these free trees and return an arbitrary monadic computation by folding over the tree. And now we can pick, for example, the state monad for M and interpret our read and write events into that state monad using get and put. So let's do it. It's actually super easy. What does the handler look like? Well, it has to take these cell events, which are sort of the syntactic descriptions, and return monadic computations over state. So for write, we just put the value, and for read, we use get. That's all of the code for doing that. And now we can plug that into our fold, general fold operation. We do have to do a little bit more work to lift the computations. So we have to, essentially, we need to lift the pure computation plus, which just returned a natural number, into the monad for state. How do we do that? Well, we return the result of our old H plus, right? So we can just use our old implementation of the handler, which in this particular case really just a matter adds the two values together. And so So to lift one monadic computation, well, pure computation into the monad, we always use return. Okay, and now that we've done that, we can write an interpreter for this monad, which has both plus operations and cell events. And we would write it as, fold the sum of those two handlers over this particular tree, which I called double. And then remember, all of the result of that will be in the state monad, right? So it will be in the state monad. State monads always take an input, the initial state, so we could give it an initial state, which is 16. And so it will read 16, add 16 to 16, and then trigger the result of writing it. And because the result of this whole computation is unit, and we're working in the state monad, we have nat cross unit as the result. And so we'll get this as the answer if we were to actually run it. And we could have done something else. We could have run the double computation, then triggered a read, and then give it 42, and that will read the result. And so rather than getting a unit, sorry, this is a cut and paste error in my comments. That should be a nat. That would give us the result of reading as the return value of the computation. Yes, question.
Do you have an example of a case where it is useful to have fold over the free monad and not just the freer monad?
Fold over the free monad and not, so a question about fold over the free monad as opposed to the freer monad. I don't think that, so I think, okay, this is, I believe actually if you had a strong enough type theory, the free and the freer monad might be equivalent to one another. Like it's just really reassociating bind. It's like Hawk as its mechanisms for ensuring termination aren't sophisticated enough to know. But now that I say that, I think you need to assume something about the functor, which is sort of a parameter of this free monad, in order to make that work. So I guess the shorter answer is I'm not sure. Immorally, they should be equivalent, and so it wouldn't matter which one you're folding. But I guess it may depend on the assumptions about the constructor of the free monad. Good. Okay. So we have 7 minutes left, but actually I-trees are pretty easy at this point. Yes, question.
So you have to write separate lifting functions for every single effect you want to support?
Right, so the question is, do you have to write separate lifting functions for every single effect that you want to support? The answer, it depends, I guess, on how complicated things are. In practice, you could use the same kind of type class tricks that I showed you for figuring out the injections to do automatic lifting if there's sort of a natural way to internalize one type of event into some other monad. Like in these cases where you're just adding return, that would be very easy to automate with some kind of type class hackery. In general, you might want to do something more sophisticated, like use the structure of one of the monads to build something more interesting in the monad you're lifting into, and then prove that it's a good lifting in some way. That would probably not be automatic. But I guess in practice, we haven't found that part to be too difficult, I would say. Good. Okay, so let me just show you I-tree. So here is the freer monad. And to get from that to I-trees, we make two moves. It has exactly the same shape. So it has the same parameter. Those are the types of the nodes. It has the return type, which will be the result of the monad. It has the return constructor, just as the freer monad. I renamed do to be viz, but actually it's the same thing. So if you look here, it has exactly the same data, except I renamed free to be I-tree. So we call it viz for some intuitions that I'll explain in just a minute. But the new thing we've done is, well, first, it's no longer inductive. It's co-inductive, which you can intuitively think of as And now the trees that we're building can be infinitely big, or equivalently, you can build a cycle that can keep unfolding forever. And we also add this tau constructor, which is useful because in order to work with these co-inductive data structures, they have to be guarded in a certain sense that guarantees that you're always sort of, you don't inadvertently make an infinite loop. And the way I like to think about these is that the tau constructors, we're using these I-trees to model monadic computations. Computations sometimes do some internal work that takes a non-trivial computation step. And you can think of tau as an epsilon transition where the system does some amount of internal work and then just continues as this tree. So they're sort of silent steps. We call them tau because often in like process calculi and so on, they're sort of not observable to the outside world. And with that kind of intuition as well, another way I like to think about the meaning of I-trees is these events E, these nodes of the tree, those are the visible events, where in some sense you can think of it as the computation pauses at some node, says, I don't know how to continue from here. Let me consult the environment, which is the handler of the interpreter, which implements the behavior. But for the purpose of the tree, we don't know how to continue. And instead, we say, we're going to pause the computation, wait to get an answer of type X, and then continue computing the tree. Of course, that's just intuition. In practice, it's you can think of it also equivalently as just an infinite tree. Okay, and here's a picture. My tree is going that way. So the root of the tree is over here. These sort of pink bubbles are the tau nodes. And they're there to just kind of give you the sense that you can have lots of them. They might be generated while you're doing computation. You could think of them as a tick of some internal clock or something like that. But they don't produce any visible events. Those visible events are these E's here, where the return type tells you how many branches there are, right? So in this particular case, E1 has 5 branches, A, B, C, D, E. And then we would call the continuation K1 on each of those branches to construct these trees. And what is interesting is that, and these sort of dark purple, those are the returns. So those are the leaves of the tree. And there's a couple of interesting situations that I-trees can have that the free monad cannot. So first of all, it's perfectly possible to have an infinite sequence of taus forever. So that is just the computation that silently diverges, never producing any visible events, and goes off into infinity, doing nothing that you can see. Could be doing lots of stuff internally. Or it might do some infinite sequence of events. So you could think of, while true print to the terminal. You could model that as these print events, and you might have an infinite number of those. And the other thing that is not that is true of the free monad and I-trees, but I didn't mention it before, is it can sort of terminate in a different way that isn't returning a value, because the result type of one of our operations could be void or uninhabited in Coq, which means there isn't any continuation that you can construct. It's sort of an empty type. You can implement that in the free monad as well. But I pointed out because it's sort of another mode of truncating the tree. And the difference between that and one of these return nodes is when you do sequential composition of these trees, those don't count as leaves, right? Only these count as leaves. They're the ones that the computation has sort of successfully completed and yielded to the continuation. This is more like an exception or an error where you aborted the computation and cannot make any further progress, so it doesn't make sense to continue after that. Both free monads and I-trees support that. Question?
So should we think of tau as an infinite loop or a skip?
So a single tau, you should think of as, so the question is, should we think of tau as an infinite loop or skip? A single tau is more like a skip. It's sort of like transition that doesn't really do anything. But an infinite number of them is like an infinite loop that goes off into forever. And in fact, where we'll pick up next time is what is the natural equivalence for these things? And the shorter answer is you can ignore any finite number of tals sort of between events that you like. You just can't ignore an infinite number of tals all in a string like this, because that would sort of say diverging computations you can ignore. And that's the whole point, is we don't want to be able to do that. Yeah?
Just a question about the D node that you mentioned. Would that be like a viz whose X is a type you can't construct?
That's right. Yeah. So, and we'll see an example of that. But if you have an event E that whose X is void or uninhabited, then yeah, that's exactly one of these D nodes. Yes, question.
I just want to do a sanity check. Does each one of these leaves represent one possible complete program that could have spawned from the original, or is this not what we're doing?
So this is, so I trees are about sequential computation, because monads are about sequential computation. You should think of each path from the start towards the leaves as one possible sequence of evaluation. And the thing is, when you get to one of these nodes, you don't know which, the environment is going to determine which. So it depends on how you interpret this. So the way, we'll see this next time when we pick up again, but basically, you know, when we interpret it in our, even in the F3, if this was the add, we had a whole bunch of continuations for it, but which one we went down depended on what two things we were adding. And so you should think of these as the possible sequential computations, and the choice of which one you do depends on how you handle those events. But I should wrap up there since we're at time. We'll dig more into iTrees starting next time, and in particular the equivalence and how we can use it to give semantics to IMP, and then go from the equational theory to reasoning about IMP semantics. So thanks.